Hello everybody and welcome to our video on some basic derivative formulas. So these are just going to be our initial derivative rules. They're going to give us some tools to work with to solve problems. So as we saw in the last section, using the formal definition of the derivative can be a little bit cumbersome for some problems. And we obviously would like to save some time. Just like, we memorize our times tables because I know that, 3 times 4 is 3 plus 3 plus 3 plus 3. That's a lot more time consuming than just knowing, hey, 3 times 4 is 12, right? So for that same reason, we have some derivative formulas that are very helpful if we memorize them. And memorizing these formulas is going to let us solve problems involving derivatives a lot more quickly. But the first thing we want to do is understand where these formulas come from. They come from that definition of the derivative. So we're going to go through some of these explicitly, deriving these formulas. And it's important to keep in mind that although you will be able to solve many problems by applying your basic derivative formulas, there are times where you have to fall back on using that definition of the derivative because the type of function you're dealing with doesn't work with any of the basic derivative formulas that we derive. So, with that in mind, we're just going to review this list of derivative rules quickly, and then we'll go through and prove some of them, and then we'll start applying them. So, the constant rule says that if f of x is just equal to a constant value, the derivative of f with respect to x is 0. So this is only true, obviously, if c is a constant. Now, although we can definitely prove this with the derivative quite easily, keep in mind that a constant value function is just a horizontal line. So the slope of this line is 0. So this should be intuitively sensible, that if you take the derivative of just a constant by itself, the slope corresponding to the tangents would be 0. Okay, so this rule is just called the x rule. If the function you're looking at is f of x equals x, the derivative of that function is 1. So again, this is another one where the graph of this function is so simple that you can see it immediately. When I look at y equals x, that's the line with slope 1, and so its derivative is 1. Now the power rule says that if f of x is equal to x to some power, then the derivative is that power, n, times x to the n minus 1, for any real number n. Now the constant multiple rule says that if y equals c times f of x, then the derivative of y with respect to x, in other words, the derivative of c times f of x, is the same thing as pulling the constant out in front and doing the constant times the derivative of f with respect to x. So this just says if you've got a constant multiple of a function, the derivative is the constant times the derivative of that function itself. Now we have the sum rule, which says the derivative of f plus g, the derivative of f plus g with respect to x, is just the derivative of f with respect to x plus the derivative of g with respect to x. In other words, you can split up derivatives on sums. Now for this to be true, of course, both f and g have to be differentiable, right? These conditions are all really important. If the conditions aren't met, then these rules don't work. But if f and g themselves are differentiable, then the sum of f and g, you can split it up to compute the derivative. Now for the difference, f of x minus g of x, well, remember the difference is just the sum of a negative, right? So it's the same exact rule. The derivative of f minus g with respect to x is the derivative of f with respect to x minus the derivative of g with respect to x. And again, we require that f and g both be differentiable. And our last two rules for this section are the derivative of sine of x is cosine of x, and the derivative of cosine of x is negative sine of x. Okay, so let's go ahead and start looking at how do we get these formulas. So first we'll just look at the proof of the constant rule. Now we looked at the picture But here's the actual proof. The derivative of f with respect to x, we're going to use the t approaching x form of the derivative here. The limit as t approaches x of f of x minus f of t over x minus t. Well, this is a constant valued function, so for whatever input I plug in, I always just get the number c back. And c minus c is 0. So this is the limit of 0, which is 0. Okay, now we'll look at the proof of the power rule, but the proof that we're going to do here only actually works when n is an integer. When we have some more advanced tools later in the course, we're going to actually see a different justification that shows why this rule works for all real numbers, right? So remember, the power rule says that the derivative of x to the n with respect to x is n times x to the n minus 1. So this rule does work for any real valued number n, but this proof only works for integers. So we'll, again, later on in the course, we'll see a proof that justifies it for all real numbers. But for now, we don't have the tools we need. So I take the limit as h goes to 0 of f of x plus h minus f of x all over h. I plug x plus h into my function x to the n. So I just get x plus h to the n minus x to the n over h. And then I have to multiply this out, x plus h to the n. So what I've done here is written this expression. We call this the binomial expansion. But what it looks like, okay, you multiply a bunch of x plus h's together, right? Your highest power is going to be x to the n because you're multiplying all the x's together. Your last term is going to be h to the n because you're multiplying all the h's together. And this is what all the terms in between look like. Now, we can prove that we get these given coefficients using the binomial theorem, which I'm not going to prove here. So if you want to look more into that, you can look into the binomial theorem. But you can do this for some small examples if you want, just to see how it works out. But let's go ahead and take a look at what we get when we subtract here. So we get x to the n minus x to the n. And so now we've got n times x to the n minus 1 h plus n times n minus 1 over 2 times x to the n minus 2 times h squared plus blah, 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 plus nx h to the n minus 1 plus h to the n. So if I factor an h out of all of these terms, I'll be able to cancel this h here. And what I get is all the terms I had up top with one lower power of h in each expression. So our first term will be n times x to the n minus 1 plus this whole thing times h plus a bunch of terms multiplied by h. And so when h goes to 0, all of these terms are going to approach 0. And we just get left with n times x to the n minus 1. Okay, so let's move on. We'll take a look at the proof of the sum rule. So this is the derivative of f plus g with respect to x. So here, when I plug this into my definition, I just get f of x plus h plus g of x plus h minus f of x plus g of x over h. And so all I'm going to do here is just a little reorganization. I move the negative f of x over with the f of x plus h. And I move the negative g of x over with the g of x plus h. And I split up my limit. I split up the terms inside along the sum. And then I split the limit along sums, which we know we can do from our earlier chapters. And then by definition, this limit is the derivative of f with respect to x. And this limit is the derivative of g with respect to x. Okay, so I think these first three that we've done are all pretty straightforward. I mean, if you're not familiar with the binomial theorem, this expansion might seem a little weird, but we understand the idea of multiplying out, x plus h to a power. It's a fairly straightforward idea. Now, this proof of the sign rule is a little trickier, and this requires the use of the special limits that we looked at in earlier sections. So let's first start with the definition. The derivative of sine of x with respect to x equals the limit as h goes to 0 of sine of x plus h minus sine of x all over h. And so here, what I've done is taken sine of x plus h and used the sum rule for sine. So you may recall from pre-calculus, sine of u plus v equals sine of u cosine of v plus cosine of v times sine of, or cosine of u times sine of v. My bad. And so if you look here, all we've done is put x and h in place of u and v respectively. Okay, so now what do we do? Well, now we just rearrange this thing slightly. We're going to pair the negative sine of x with sine x cosine of h. And we're going to move the cosine of x sine of h separate. And once we do that, we just split the fraction up. So now we've got two fractions here. Sine of x cosine of h minus sine of x all over h plus cosine of x times sine of h over h. And now I'm going to write these slightly differently again. For this first fraction, I factor out sine of x. I get sine of x times cosine h minus 1 over h plus cosine of x times sine h over h. So sine of x and cosine of x here, our limit is in terms of h, so x is going to be treated as a constant here. So when I look at sine, the limit as h goes to 0 of sine of x, and the limit as h goes to 0 of cosine of x, those limits are just going to be sine of x and cosine of x, respectively. But the rest of our expression are the special limits from before. So this is the special limit for cosine, which we've proven equals 0, or we've seen equals 0. And we proved explicitly that this special limit for sine is equal to 1. So we get sine of x times 0 plus cosine of x times 1 equals cosine of x. So that's our derivative rule for sine. Okay, so we've proven quite a few of these. So what did we go through? We proved the constant rule, the power rule, the sum rule, and the sine rule. So I'll leave the proofs of the others as an exercise for yourself. Let's go ahead and take a look at applying these rules to some derivatives of functions. Now, one thing that I want you to do when you are first starting these first few sections of derivatives, it's very important that you write down what rules you use when you're using them, because it's going to help you keep your work a lot more organized and easy to follow when you go back and try the problems again later, or when you go back and try to figure out how you solved certain problems. So for example, here, this is a constant. So I'm just going to say, hey, this derivative is 0, and I'm just going to note that I used the constant rule. And then we move on. Now I'm looking at this function g of x equals x to the fourth, so I want the derivative of g with respect to x. And this is 4 times x to the 4 minus 1, or in other words, 4 times x to the third power, and that's just the power rule. So remember, again, the power rule, you're going to use this one a lot. The derivative of x to the nth power is n times x to the n minus 1. Now for this one, we want the derivative with respect to x of negative 5x to the 7th. But this is a constant multiple. We have negative 5 times x to the 7th. So we can pull that constant multiple out in front and then look at the derivative of x to the 7th. So this first step here is the constant multiple rule. So don't mix it up with the constant rule, right? This is a multiple of a function, and the multiple is a constant. The constant rule is when the whole function is just a constant. All right, and this gives me negative 5 times 7 times x to the 6th. Again, that's the power rule. N times x to the n minus 1. So this is negative 35 x to the 6th. And I'm just going to note here that I used the power rule. All right, we got plenty more examples to go through, so let's continue. Here we've got the derivative with respect to x of x minus sine of x. That's the derivative with respect to x of x minus the derivative with respect to x of sine of x. So the first thing I've done here is just the difference rule. I can split up my derivatives on differences. And now I'll compute each of these derivatives. The derivative of x is 1, and the derivative of sine is cosine. So this is the x rule and the sine rule. Now, for this next one, cosine of x plus the square root of x, remember, we don't have any radical rules, but our radicals are really just fractional powers. So the first thing I'm going to do is just rewrite the function as cosine of x plus x to the 1/2. So now when I write out my derivative, I'll have this as a power, and I can apply the power rule. So, but first, I've got a sum between these two functions. So we'll split up the sum. So that's our sum rule. And the derivative of cosine is negative sine of x. And the derivative of x to the 1/2 is 1/2 times x to the negative 1/2. So this is the cosine rule and the power rule. And now I'm just going to rewrite this slightly. It's not necessary, but typically we won't leave things as negative powers. We'll write them as 1 over that power. And furthermore, you'll often see these rewritten back in terms of radicals. So this would be 1 over 2 times the square root of x. Okay, so far, so good. Now, in this next step, we have a product of two functions, but none of our rules deal with products of two functions. We will deal with that in general in a later section, but that's actually quite a bit more complicated. So we don't want to have to deal with products of two different functions. So how can we deal with this? Well, what we can do is first distribute and multiply everything out. So let's just rewrite our function. So we get x cubed plus 3x plus x squared plus 3. None of these powers are the same, so I can't combine any terms, so I won't bother with that. But now if I want my derivative of this thing, I can split up the sum. Okay, now I'm going to do one little thing here. I wrote the derivative of 3x with respect to x. I'm going to go ahead and move the 3 out of that derivative. So essentially I've done two things here. I've done the sum rule and the constant multiple rule. And so now I apply the power rule here, I get 3x squared. I apply the x rule here, I get 3 times the derivative of x, which is 1. I apply the power rule, I get 2x. And here I apply the constant rule, which is 0. So what did I get? I got all of these were the power rule, the x rule, and the constant rule. So power rule, constant, and the x rule. So I'll just rewrite this in our standard form, 3x squared plus 2x plus 3. Okay, so far so good. Let's take a look at another quick example. We've got g of x equals negative 2 over x to the 5th. So first I'm going to rewrite this as negative 2 times x to the negative 5th. Now I have a nice x to a power. So when I go to apply my derivative rules, first I'll get negative 2 times the derivative with respect to x of x to the negative 5th. That's negative 2 times negative 5x to the negative 6. Remember, we multiply by the current power, or the original power, and then we subtract 1 from it. That's our power rule. This gives me 10x to the negative 6th, or 10 over x to the 6th. Okay, so far I've dealt with all of these problems using Leibniz notation. Again, oftentimes students will come in a little bit familiar with derivatives and they'll only be used to prime notation. So I want students to get really comfortable dealing with Leibniz notation first, which is why I've written all of these this way. But now I'm going to go back and just do a couple of these, and I'm just going to write them the work. I'm not going to rewrite the statement of the rules. I'm just going to rewrite some of the work using prime notation. So here, I might say that 27 prime equals 0. Or x to the 4th prime equals 4x cubed. Here I might say negative 5x to the 7th prime equals negative 5 times x to the 7th prime, which equals negative 5 times 7 x to the 6th, which is negative 35x to the 6th. So typically prime notation does make things a little quicker to write. But as I said again, later on in the course, there will be times when prime notation will actually cause confusion on certain topics because it's not as clear. So we really do want to get as comfortable as possible using both, which is why, again, I did everything first with Leibniz notation. Okay, so I did those examples with Leibniz notation. I imagine you can see the idea here, so I'm just going to go ahead and move on. All right, now we're going to graph both f of x equal to x to the 4th and the tangent line of f of x at the point 1, 1. Okay, so first let's figure out what the tangent line is. Well, for that, we need to know what the derivative is at x equals 1. So f prime of x is just 4x cubed. That's the power rule. But that means f prime of 1 equals 4 times 1 cubed, which is 4. And so now when I go to find my tangent line, y equals f prime of 1 times x minus 1 plus f of 1. That's going to give me y equals 4 times x minus 1 plus 1. That's 4x minus 4 plus 1, which finally gives me y equals 4x minus 3. So that's my tangent line. All right, so let's try to sketch this thing roughly. So I'm just going to go out 2 in each direction and plot a couple key points. When I plug in 0, I get 0. When I plug in 1, I get 1. And likewise, when I plug in negative 1. And when I plug in 2, I'm going to get 16. So we're just going to kind of jump up here to 16. And it might not be perfectly to scale. That doesn't really matter. Now, Our tangent line at 1, 1 is going to be the line that passes through the point 1, 1 on the graph. And it has slope 4 and y-intercept -3. So there we go. That's our tangent line at the point. And there's our function. Okay. Let's go ahead and move on to another example. The position of a particle is given by f of t equals 1 plus t squared with t in seconds. Find the velocity of the particle at time t. Well, if f is the position function, then the velocity function, by definition, is f prime of t. And that's going to be 1 plus t squared prime, which is 1 prime plus t squared prime, which is 0 plus 2t, which is 2t. So we had the sum rule, and we had the constant rule, and we had the power rule. All right, find the velocity after 3 seconds. Well, v of 3 is pretty straightforward. That's 2 times 3. Just plug into your function. That's 6. When is the particle at rest? When is it moving forward? When is it moving backward? So in this particular case, this is pretty simple. Don't overgeneralize this. It will not always be this nice. But what do we see? V of t equals 2t. So this is going to be positive for positive values of t. All right, because a positive times a positive is positive. And v of t is going to be negative for negative values of t. And v of t is going to be 0 for t equal to 0. So when t equals to 0, this is at rest. The particle isn't moving if its velocity is 0. And when the velocity is positive, by definition, that means it's moving forward. It's moving backward. Now, it may sound odd to refer to negative times, so I want to be a little clear about that. When we say t is less than 0, that means with respect to a reference time, right? This equation may be looking at a particle that's been moving forever, but maybe we set 5 p.m. on a Friday as t equals 0. So if we want to look at what was happening to that particle before 5 p.m. on Friday, we would be looking at negative values of t in that context. All right, well, that's it for this one. Let's move on to another topic, and this is the idea of marginal cost. So this is an idea from economics. Suppose, or business really, suppose that C of X is the total cost a company pays to produce X units of an item. Then the average rate of change in cost per item is given by delta C over delta X, which is C of X minus C of T over X minus T. Taking the limit as delta X goes to 0 gives C prime of X equals the limit as T goes to X of C of X minus C of T over X minus T, which is the instantaneous rate of change in cost with respect to the number of items produced. So we call this marginal cost. So this is an example of a derivative that isn't with respect to time. Here our variable is the number of items produced, and we're taking this derivative with respect to that. Now there is something a little funny that's happening here because, of course, for most objects being manufactured, you can't produce a fraction of the object. It doesn't make sense. So these functions aren't truly continuous, but these cost functions that are so typically you would only be doing X as integer values, but we can still approximate these behaviors using continuous functions that would accept any value of X. And we're going to look more closely at that in this example. So a company estimates the cost to produce X items as C of X equals 25,000 plus 10X plus X squared over 2. Find the marginal cost function. Then find the marginal cost for the 300th item and compare this to the actual, not actually, let's go ahead and fix that, to the actual cost of making the 301st item. Okay, so compare this to the actual cost. Oh, so what do we mean by that? Well, what I mean is I want to find C prime of 300. Right? That's what we call the marginal cost. Marginal. But what's the actual cost going to be? Well, that's the difference in paying for 301 items versus paying to manufacture 300 items. That's how much the cost went up producing one extra item, right? So let's first find our derivative. So we've done a bunch of these derivative examples, so I'm gonna do this one kind of in my head a little bit. The derivative of 25,000 is 0. The derivative of 10x is 10 times the derivative of x, which is 1, so that's just 10. Plus 2x. Remember, x squared over 2 is really just 1/2 times x squared. So it's 1/2 times the derivative of x squared, which is 2x. So this is 10 plus x over 2. So in other words, the marginal cost to produce 300 items or the marginal cost, I should say, to produce one additional item after producing 300. That's the way we express this idea. How much additional cost will it take to produce one more item after we've produced 300? It's just 10 plus 300 over 2, which is 10 plus 150. Oh, wait a second. Hold on. We made a little mistake. The 2 over 2 cancels. That should just be x there. 2 times 1/2 is 1. Shocking. So this should be 10 plus 300, which is 310. Okay, that's our marginal cost. Now let's look at the actual cost. So for this, we get 25,000 plus 10 times 301 plus 301 squared over 2. Actually, let's go ahead and we'll move that here, give myself a little more room. Minus 25,000 plus 10 times 300 plus 300 squared over 2. I could use a calculator for this, but I'm going to show you that you can actually get away without using a calculator for this if you just use a couple little clever algebra tricks. So the first thing is the simplest one, 25,000 minus 25,000. It's nothing. But I see these 301s, and these are the same thing as 300 plus 1. So I'm going to rewrite this as 10 times 300 plus 1 plus 300 plus 1 squared over 2 minus 10 times 300 and I distribute that negative, and I get minus 300 squared over 2. Okay, so why did I do that? Well, because when I distribute this, I get 10 times 300 plus 10 plus, and when I multiply this out, I get 300 squared over 2 plus 1 times 300 plus 1 times 300, that's 600 over 2, plus 1 times itself, which is 1 over 2, minus 10 times 300, minus 300 squared over 2. Again, if you wanted to use a calculator for this, it would be okay, but look, we can just cancel that and that. And 300 squared over 2 cancels with negative 300 squared over 2. And so then we've got 10 plus 300 plus 1/2, which is 310.5. So again, as we said before, these cost functions are only defined for integers, so they're not quite right. They're not truly differentiable when you're restricted to only the integers, and as such, when we look at these marginal cost approximations, they don't give the exact answer, but they give a very close answer. I mean, 310 versus 310.5 is very close, and look at the difference in the amount of work we have to do to compute these two values, right? So especially when you're looking at huge numbers of things being manufactured, millions upon millions of items being manufactured, when you look at those kind of numbers, it is so much more efficient to calculate with marginal cost, and it'll be accurate to with any reasonable accuracy that's needed. Okay, so that's it. That's the idea of marginal cost, and we've tackled some basic derivative formulas. So thank you everyone for watching.